Okay, good day, everybody, and welcome to AeroVironment. Great to be with you, and thank you for joining us this today, both physically here in this building as well as virtually through our live stream on Vimeo. Today is a very exciting day for me because we're going to be able to share with you one of the many groundbreaking and exciting innovations at AeroVironment, specifically related to the Ingenuity Mars helicopter, which has now flown so far multiple times on the atmosphere of Mars. And so our team at AeroVironment, who helped develop this and make it a reality for us and for the world, is with us today, some of them, and they're going to share some of the stories there. Before we get into that, I wanted to just share with you a little bit about AeroVironment. We're a technology solutions provider at the intersection of four future-defining capabilities and technologies, namely robotic systems, sensors, highly sophisticated sensors, analytics and AI and machine learning algorithms, as well as connectivity. We take these defining technologies and we fuse them together and integrate them and create these wonderful, wonderful innovations and solutions for our customers, both domestically and abroad. We serve 50 different countries around the world. We're the leading provider of unmanned systems, both on ground, air, as well as on a stratospheric level now, and even on the submaritime level, on submerged from the water, for both defense, civil, and commercial markets. We serve all three markets globally. So one of the fascinating and exciting things about AeroVironment is that many of the innovations and learnings that uh, we are involved in various different development of products for our customers here on Earth turns out to actually help us in many other projects all over the world and also even on Mars. So the building we're in here, you see in front of me, behind you, we have some specific sections, two of the 7 sections of our solar stratospheric airplane called Sun Glider. This is obviously an airplane that AeroVironment designed and developed here. This is the one of the later generations of this capability, which last fall we flew. One of the latest flight was we achieved about a 60,000 plus, I think it was 62,000 plus square feet, feet above sea level, not square feet, 62,000 plus feet above sea level in Spaceport, New Mexico, and it was carrying an LTE payload and essentially broadcasted a cellular telecom communication, and I was able to make a Zoom call from my smartphone from Earth through Sun Glider to Tokyo, Japan, Washington, D.C., and Northern California. So designing for environments such as the stratosphere and designing systems like you see behind me for rugged terrains of dust and high extreme heat and cold temperatures around the world here on Earth really has helped us develop the solution for the Mars helicopter Ingenuity for NASA and JPL. So many of the learnings that we've had for years helped us and informed us to be able to do this. And our team is going to share a lot more about that with you today. Similarly, I'm a firm believer that the learnings that we're getting now today on the development as well as the operation of Mars Ingenuity will inform us and help us develop future solutions for other customers around the world, whether it's ground robots or UAVs or other systems for both domestic, commercial, international, military, or even non-military applications. So without further ado, I'd like to introduce the first member of the team, or one of our chief engineers, a talented guy by the name of Ben Peipenberg. Ben, why don't you come to stage and now help us, tell us more about the development of the Ingenuity and what challenges you took and what things you had to do to make this thing fly on the atmosphere of Mars.
Yeah, absolutely.
Thank you.
All right, thank you, Wahid. Good morning, everyone. So as Wahid said, my name is Ben Peipenberg. I was the lead engineer for AeroVironment's portion of the Mars helicopter program. Um, as Wahid said, we've been a member of the Ingenuity team since 2013 when JPL first approached us to ask for help designing and building rotorcraft for Mars applications like this. In those early days, there was actually a lot of skepticism, even within the aerospace community, that something like this would be able to work. And there's a good reason for that. It's a very difficult engineering problem. The atmosphere on Mars is very thin. there is an atmosphere, but it's similar to Earth at about 100,000 feet above the ground. And so because of that, Ingenuity must have very large rotors that spin much faster than they would here on Earth. And it needs to be very lightweight. The whole helicopter needs to be very light to fly in that thin, tenuous environment. But as Wahid said, we've had a lot of experience with this in the past. Some of the earlier high altitude pseudo-satellites, similar to Sunglider, have flown at over 96,000 feet, which is very similar kind of an environment to Ingenuity. And so we were able to pull a lot of that experience into developing this aircraft, and now we're being able to take some of the lessons learned on Ingenuity and reapply that to the next generation of atmospheric satellites. But in addition to being a very highly optimized helicopter, Ingenuity has to be a very capable spacecraft as well. It needs to survive these very harsh launch environments. Launching on a rocket's really a very difficult thing for a lightweight structure like this. And once it's launched, it needs to survive the vacuum of space for 8 months as it's flying to Mars. And once it's on Mars, it needs to survive the very blistering cold atmosphere overnight. It gets down about 150 degrees Fahrenheit below zero. It's very dusty. It's being bombarded with radiation continually. And so it needs to be very robust, and it needs to do all of these things very reliably. We can't just go pick it up because it's 200 million miles away. And so it needs to do all of these things 100% of the time, 100% perfectly. And so what the team's going to be talking about here today are AeroVironment's contributions to the Ingenuity project. And to help us with that, here we have Terry, the terrestrial helicopter. The airframe on Terry is virtually identical to what's currently on Mars with Ingenuity. The structures, the composites, the mechanisms were quite literally built from the same molds that we used to build Ingenuity. But Terry's designed to fly here on Earth. And so the motors were redesigned to be more powerful, to have higher torque, to handle the denser atmosphere here and the higher gravity. And it doesn't need to be a spacecraft. And so it's using more conventional avionics, similar to what we would have here for some of our applications. And we'll be flying this a little bit later, so you'll get to see what that looks like. But first, we have some of the subject matter experts who have helped to develop a lot of these systems. And so they'll be highlighting some of the components on here that AeroVironment designed and built. And that includes the solar array substrate, this composite structure here at the top, the rotor system, including the rotor blades, the hubs, the propulsion motors, control mechanisms right here in the middle, the landing gear at the bottom, which needs to fold to fit onto the Perseverance rover, and then this box at the bottom, which is called the helicopter warm electronics box. And that is an insulated structure that helps to keep the avionics, the batteries, and the sensors that JPL designed and built warm overnight. But maybe none of the components on here are quite as special and as unique as the propulsion motors that spin the rotor blades. And so to talk about that here today, we have Matt Keenan. Matt's the technical lead for AeroVironment's Mars helicopter program. So I'll hand it over to you, Matt.
Thanks a lot, Ben. So I guess I'm the old timer on the team. I've been at AeroVironment for 25 years, and I started on the Ingenuity project in 2014. And I've worked on a lot of very difficult flying machines over those years. But the propulsion motors and the actual wiring inside of the mast of the Ingenuity helicopter were two incredibly challenging tasks that I took on as part of this project, as well as doing other things. So the propulsion motor is right here, and it's attached to the rotor blades. And the difficulty we had with the propulsion motor was it was a flow down of requirements and challenges that came from JPL's limitation on the size of the helicopter. So we have the limitation of this distance right here, where we have to have two duplicate sets of rotor system components, the propulsion motor, the blade, the mechanism, the actuators, and then a duplicate system. And I think it was around 2016, we were starting to put together the design elements, and the team found that it wasn't enough vertical height to fit everything. And pretty much the only option was to make the motor smaller. We started with a motor design that was about half-inch thick, and that was a really excellent motor. It was optimized, but we couldn't fit it in with all the other systems that absolutely had to fit in there. So we ended up talking as a team, what were the options, what were the trade-offs, because going to a smaller motor, it's typically less efficient, and then it's going to have more waste heat, and there's a huge problem on Mars shedding heat because the atmosphere is so thin. We're used to having the air around us, and we get hot, we just dissipates into the air. But on Mars, it's a particular problem, and it's a particular problem with the motors on Ingenuity, because they're enclosed and the actual heat generating elements are inside a carbon fiber casing. So Bart Hibbs was the motor designer for our Mars helicopters, and he presented to the group the option of making this motor about 1/4 inch thick, and this is one of the actual stator parts from it. But the problem was it would have to be larger in diameter than the original design, which would add complexity to the housing, which Ben would have to deal with. And then a really big problem was it would be less efficient, so it would have more waste heat. And then we have that problem of getting that heat somewhere. And we had to actually store it in the structure. And that was a huge task that Ben took on as part of the structure in the middle of the motor. But even at that efficiency, there was a complexity that Bart said, you can have your 1/4 inch high motor and it can meet the specs, but it's going to be a motor with copper windings like we've never done before. AeroVironment has a long history going back to the 1980s of designing and actually fabricating customized optimized motors for different vehicles. And we had never fabricated a motor like this. And the nitty-gritty is the copper has to be very much filled in between the iron teeth. And the more copper you get in there and less air, the more efficient the motor is for its given size. And we had this 1/4 inch height limitation. So I naively volunteered myself, talking to Bart and saying, well, we should be able to pack those wires in as tightly as your spreadsheet says they can actually fit. And I had wound motors a couple times before, and it's like, yeah, it sounds like fun. I'm pretty good with working under the microscope. So what we had to deal with was a shift from round wire to rectangular wire, and this very tight packing, very tight winding of a fairly thick wire. And this is actually copper wire that's rectangular, and it's insulated with a very thin film. And it has to be wrapped around these iron teeth, which are a stack of fairly delicate iron sheets. And it has to be done absolutely perfectly. Each tooth has 7 wire coils around it. So if you think about this being rectangular, the cross section looks something like this. So if you wind it around the tooth, you have the next one coming up here, and then the next one coming up here, and so on. But these are not separate wires. It's one continuous wire that you pull around in a helix. And when you do that, rectangular wire wants to tilt. And if you have a coil that's tilted like this, and it's wound around the tooth, it's extra tall this way, and it's actually spaced this way. So the next one you put over here is spaced further out. And Bart designed this for optimization, and it's 7 of these tiles all in line perfectly, and there's not even room for the thickness of a piece of paper on the end. So we cannot tolerate this. We can tolerate kind of like that, just a little bit of a tilt on one turn. So I had to develop little wedges and different hand tools, and then a motorized system to wind these guys pretty much perfectly. And this is my first practice piece. If you get a chance to look at it or zoom in with your camera, some of these windings are really, really quite bad. But this was my first attempt, and just getting a feel for the wire, getting a feel for the iron. And after this, I worked out a system, had all these little pieces, and I ended up making the first motor that we delivered to JPL. That took 100 hours to fabricate the entire motor, and just the twisting of the wires was 80 hours. And then we did 6 additional motors, and the last 2 were the ones that went on to Ingenuity, and they're on Mars. So I actually wound those in my office. And we kept it very clean, but it was a very difficult task. And then Terry here has 2 more motors that I made more recently, and they're slightly different, but they're fundamentally the same. And I hope you get a chance to come up and look at Terry, because we actually left the top of the motors open so you could see these coils, and you'll actually be able to look at it and see which ones of these are all flat and which ones are just slightly up. And so when I look at that, it's like, oh, okay, there's one that's a little bit off. But in the end, the motors hit their design specifications. Bart did an excellent job with the design, and the assembly, the fabrication that I did worked great. They were dynamometer tested, and they've been obviously working extremely well on Ingenuity on Mars. We're looking at the data from the motors, and it's all within nominal ranges, so we're extremely happy about that. I worked on a lot of aspects of the Ingenuity helicopter and some of the subscale models, the earlier developmental models. And I was going to talk about the wiring, but I think I've kind of gone a little bit over time. So if you want to hear about the challenges of installing wiring inside of the Ingenuity mast and the branches, just ask me during the Q&A session. But now I'd like to introduce Sarah Langberg to talk to us about the challenges of designing and fabricating the composite parts on the Ingenuity helicopter.
Thank you, Matt. My name is Sarah Langberg, and I'm an aeromechanical engineer on the Mars helicopter program. And I worked on many aspects of Ingenuity, but I'm here today to talk to you about, most notably, our composite structures. So one of the greatest design challenges we had when designing and fabricating Ingenuity is that it has to be extremely lightweight, but also strong enough to withstand launch loads and stiff enough in order to be controllable in the Martian atmosphere. And in order to do that, we employed extensive use of advanced composite materials. And Ingenuity has many custom carbon fiber components that were designed, molded, fabricated, and tested all here at AeroVironment. And many of those you can see here on Terry. These include the backer of the solar panel, the blades, the motor housing, the mast tube, which is the backbone of the vehicle, the landing gear, and the structure of the H-wing. So the rotor blades are a composite structure of an engineering foam and carbon fiber. And we take carbon fiber spar caps and skins, we lay them over the foam core, and we place them in a mold in the oven. And when they come out, we have this finished part, which is extremely lightweight, but also very stiff. Hold it right here. You can hear how stiff it is. And so having these be both light and stiff is critical to Ingenuity's performance. And then another issue we had when designing the main structure is that it has to be strong enough to survive launch on a rocket. And that's a very violent event. And when Ingenuity is stowed for its trip to Mars, it's held by the ends of the mast, which is the central backbone of the vehicle that all the other components are mounted to. And it's held by the ends like this with all the weight in the middle. So due to the shaking of the rocket, this one component has to be very, very strong. And we were able to use composites and get creative in a way to strengthen the part without making it too heavy. And so if you can see, the inside of this tube has like a flower shape to it, and it has these flutes that run along the length of the tube. And this allowed us to strengthen it locally without making the part heavier overall. We had a lighter overall system. And then the landing gear really highlights how we can use composites to work with really organic part geometries. So when Ingenuity is stowed underneath the Perseverance rover, it has to fold up very small for transport. And so all the legs fold up next to the solar panel and the blades. And they all had to be held in a slightly different position based on where they were allowed to be under the rover. And so all 4 legs are held in a different stowage position, which resulted in different deployment angles. And because of that, the shoulders of the landing gear here are all in 4 different positions. And the landing gear plate, which is housed under this film, is a very organic part. And using composites and molded parts allowed us to work with these very difficult geometries. So when the blades are, or when the legs need to be stowed, they're folded up like so and held up here by the ankle. And then when we're ready to deploy Ingenuity down onto the surface, we release the legs and they latch into place like so. And Ingenuity is ready to perform its surface missions, and it's ready to go. So to tell you more about the landing gear and all the mechanisms, it's my pleasure to introduce Jeremy Tyler.
Thank you, Sarah. So I'm Jeremy Tyler. I've been designing aircraft for AeroVironment for the last 14 years now. But have to be a part of the team that designed the first aircraft to fly on another planet is by far the most amazing project I've been involved in so far. I designed many of the intricate mechanisms on Ingenuity. So starting with the servos, there's a trio of servos for each rotor head. And they're very highly optimized, very lightweight, strong, precise. And in the middle here is a very specialized titanium swash plate that transfers the servo forces through this series of linkages up to each rotor head. So there's 2 identical copies, 6 servos in total. And every single component on Ingenuity, and especially the mechanics here, had to be extremely optimized for weight, for strength, for stiffness, for thermal expansion, for reliability, and of course, dust tolerance. One of the structures in particular that I'm most proud of, though, is this very distinctive hoop shape at the shoulder of each landing gear leg. So the core of that structure is this titanium member here, and it serves many purposes. So first, it's the hinge about which each leg folds up, and each one of these is unique as each leg folds at a different angle. At the root here, there's a pair of redundant latches that locks each leg into position, as Sarah just demonstrated. And this lower curved section is actually the spring. And this is the suspension spring for the entire helicopter. So you can see it has quite a bit of travel. This part will bend by about 17 degrees and gives the helicopter a total of 3.5 inches of vertical travel. So it can absorb even the hardest of landings. And at the top, this corresponding hoop is an aluminum damper. And it buckles and fatigues with each landing. It functions kind of like the crumple zone on a car, and absorbs that landing impact energy and prevents the helicopter from bouncing after each landing. So then this spring pulls that back into shape after each landing to prepare it for the next. And to demonstrate a hopefully much softer version of the Martian landings, I'm going to bring Matt back up, and he'll do some exciting flight demonstrations for us.
Thanks a lot, Jeremy. That's awesome. All right, so I think we mentioned this helicopter here. It's nicknamed Terry as an abbreviation for terrestrial version of Ingenuity. And we discussed earlier how it was slightly different from Ingenuity. It has taller motors that are capable of producing twice the amount of torque compared to Ingenuity. And we also reduced the weight of Terry compared to Ingenuity because it's flying in Earth's gravity. And the reason we built this was kind of two purposes. One, for educational applications, and then also for future Mars helicopter research. So we kind of have those two aspects going. The educational aspect is why we have the replica solar panel on the top of the aircraft. Okay, so I'm actually going to power it up while I'm giving a little overview, because it takes a moment to self-initialize. And so again, we have oversized motors, but the rotor blades are the same, the linkages are the same, the landing gear is the same, and then we had to come up with a different solution for the JPL components, obviously, because this is entirely built by AeroVironment. Okay, I think that's the short story. Yeah, let's go ahead and do it. If we can clear the table and the chairs away. And we'll just leave one microphone. And we'll go ahead and do a flight demonstration and see if... Okay, so this is manually controlled. I have a hand controller here. Ingenuity is all pre-programmed, automatically controlled through a script. The functions are the same, though. It has the up-down control, rotation left and right, and then it can slide in any direction. All right, so I'm going to go ahead and start the flight sequence here. Spinning up. Let it come up to flying speed on the rotors, and I'm going to do a little bit of flying similar to Ingenuity, and then I'll just kind of buzz it around a little bit freestyle. All right, lifting off. Simple up-down flight, like Ingenuity's first flight. Second flight. Time, and then two laterals. And then came back to its original landing spot. And this is very much what Ingenuity would look like flying. So it has the same characteristics. And this is just giving you a little idea in forward flight, show you what it looks like from different angles. This is about the top speed that Ingenuity flew on the flight before. All right. And that's Terry flying for you. It worked well. All right. Let's see. I think the next step is what, the Hummingbird? I think that's the plan. Sarah, you want to grab the aircraft? Then you got the bird. So much. That worked out really well. The next thing we're going to show you is the Nano Hummingbird. This is a little robotic hummingbird that was developed and built by AeroVironment from 2006 to 2010. It was funded by the US government through DARPA. And many of the same team members that worked on Ingenuity also worked on the Nano Hummingbird. And the goal of this was to research the feasibility of building a man-made flapping wing aircraft that could hover with only its flapping wings, and it would also look like a bird. And again, this was built in 2010. All this hardware is from the original DARPA-funded project. And it has very similar controls to Terry, so it can fly up and down, rotate on its axis, and then fly in any direction, or any combination of those commands. So I'm just going to turn it on here, do some pre-flight checks. And so Ben worked on this project with me when he was a summer intern in 2010, I believe. Yeah, it was towards the end of the program. And he and I worked on developing some of these techniques of making very lightweight, optimized mechanical structures. And it's making compromises. You can't have just one perfect actuator and then drop it into a lightweight structure. You have to make the actuator part of the structure and optimize it as a system. And Ben does that with his model airplanes, and he came on board as an intern, and it was a really good experience. And then, came on full time and did the Mars helicopter project instead of getting his master's degree. All right, so let's see if little bird's going to perform for you. So again, we have the up-down control, the rotation, and then we can fly sideways. It still makes me smile. This thing is awesome. And then go up, do a little ballet pirouette. And it does have a small video camera, but we're not sending that out yet. We're not running it today. So that's a Nano Hummingbird. Let me try taking off. Maybe wants to say hello to you guys. It's a little bit tired. It's over 10 years old, so I think that's enough for today. The Nano Hummingbird by AeroVironment. All right, well, so yeah, we're going to bring the table back.
That's good. Okay. Thank you, Ben, Matt, Jeremy, Sarah, and the rest of our team. Obviously, this is just a small sample of the larger team that worked on these incredible and fascinating innovations. So thank you for what you've done for humankind. Thank you for what you've done with the helicopter and obviously all these other exciting things. It's such a joy to come to work here every day because you're surrounded with these incredible, talented folks, engineers and scientists, and also these incredible innovations and programs and projects at AeroVironment. Similar to how they have helped Ingenuity proceed with certainty on Mars, they're helping all of our terrestrial customers here on Earth proceed with certainty, whether they're in the defense and military, men and women in uniform, or farmers in the field, or they're civilians dealing with emergencies and responses to those kinds of events. So that's what we do for a living as a company. And that's what gets us up out of bed every day to come here and do these incredible innovations and apply to these extreme conditions such as Mars or the stratosphere or the military in extreme cold and hot and dusty conditions around the world. With that, I'd like to welcome the team back to the stage, and I also want to thank all of you for joining us both virtually as well as in person here and taking the time out of your day to hear the story and learn more about Ingenuity and about the innovations and the challenges that our team had to overcome to make this a reality. And so far, this helicopter is performing fabulously in Mars, from what I understand and hear and read. And so we look forward to the future of this. And I'm sure some of the learning here is going to be applied to future programs and future innovations and creation of our teams and for our customers. With that, now would like to open up the final session or part of the session, which is the questions and answers. You can ask questions here physically in person if you're here, or you could also ask the questions through the virtual platform Vimeo on live stream as well, and we will take those questions as we go. Yes, we will be available for one-on-one interviews or discussions later as well. Yes. The microphone.
One question that has come up, what happens with the experience in the stratosphere that informs the ability to design and develop a helicopter like this? What were those technologies and those learnings? Thank you.
Yeah, sure. So, you know, as we mentioned earlier, there was quite a bit that we were able to pull from our AeroVironment's experience with the high altitude pseudo-satellite platforms, solar powered airplanes that fly up to around 96,000 feet. The atmosphere is very similar. The radiation environment is actually somewhat similar as well. We're outside of the protective magnetosphere that we have on Earth for the most part. And so we're able to pull some of the motor design from that, the motor controller design. The aerodynamics are very similar as well. The atmosphere looks quite the same. And so the tools that were developed to design those propellers and analyze those propellers for some of the early solar aircraft were directly used for Ingenuity. And now some of the tools that were developed for Ingenuity are going into that next generation of solar-powered aircraft, sun gliders and others.
Hi, I noticed the Hummingbird has such interesting flapping wings. Was it helpful at all, any of the technology for that, for going towards the rotor?
Yeah, sorry I didn't talk about that more earlier. I did mention a lot of the team members that worked on the Hummingbird later worked on the Ingenuity helicopter program, and not particularly with the flapping wings. These are more like sailboat sails than they are rigid rotor blades. But it was really the skill set of designing the mechanisms to work with the aerodynamic specifications for the wings and optimizing this whole system development, and not just taking the best piece here, the best piece there, and then putting it together and trying to make it fly. The whole system had to be designed in parallel. So as a technical lead on the Hummingbird project and on this project, it was very important for me to have weekly team meetings with the engineering staff, and we all hash out and talk about what problems we're having, because we all need to solve those problems together. It's not just the motor guy's problem if the motor doesn't fit. You know, it needs to work with the mechanical engineer, the thermal, the electrical engineer. And when it's this difficult, when it's this cutting edge, those types of problems and discussions become very, very intense, because oftentimes engineers just want to give me my requirements and I'll do it. But with stuff like this, the requirements change, right? I mean, it's a constant flow, and JPL might discover they have an issue with something, and then we have a slight different requirement. So it was more the skill sets that the team members developed than specific technologies that transferred. But I don't know, do you want to add anything? You want to say, so a summer intern?
Yeah, yeah, that's right. 12 years ago, summer intern. Yeah, so I mean, Matt covered it essentially, but you can kind of, if you come up, you probably can't tell from back there, but if you come up and take a look at this, this is a very tightly integrated mechanical system, and that's exactly what Ingenuity is. It's very mass constrained. It needs to be pretty reliable. This thing is flapping at 40 hertz. The loads on it are very, very high as well. And so, some of that experience and some of the tools that were put together to develop this kind of a very highly integrated, complex mechanism fed directly over to Ingenuity. Okay.
We have some questions coming in online here. Did the materials you use for Ingenuity differ from what you usually use on Earth?
Sure. Yeah, absolutely. So there are a number of fairly unique, pretty exotic materials on Ingenuity. Using composites for all of the primary structures on a spacecraft is fairly new. It's being done more often now. But there are a number of places where this was absolutely critical, right? Getting the rotor blades extremely lightweight, getting the primary structure, the landing gear extremely lightweight, but also extremely strong, is absolutely an enabling technology for flying on Mars. And so developing some of those techniques was really critical. And same thing with the motors. There's aluminum, beryllium, metal matrix materials in the motors, very specialized steels all across it, specialized titaniums, and ceramics for a lot of the ball bearings, full ceramics rather than metals. So yeah, all of those materials had to be analyzed and developed for these very specific applications in specific environments.
Did you want to mention the composite, the carbon prefrag is slightly different than what we would use for a run-of-the-mill?
Sure. Yeah, sure. So some of these composite materials, the carbon fibers that we're using, the techniques are pretty similar to what are used for terrestrial applications, but the materials themselves were developed by Toray Advanced Composites, which they're used pretty heavily for spacecraft, and they're very unique in that they're specifically designed to meet some of the low outgassing, radiation, very cold environments that we have in space as well as on Mars. And so we made quite a bit of use of that working with Toray to put those into production for this aircraft.
Is the epoxy special because it's getting a lot of sun exposure? I can't remember if that was, no, the matrix. Okay, cool. All right, any other?
Next, we have time for just two more questions. Does Terry have a camera on it? And if not, are there plans for integration of a camera system?
Yeah, so that's an excellent question. So Ingenuity has two cameras, one that's facing out and down, and then another one that's facing straight down for navigation. And we wanted this to look like Ingenuity as much as possible. So we did set up Terry with the outward-looking camera. It's a simple, analog video camera that's looking out and down. We haven't installed a camera on the bottom yet. We might do that in the future, but we just didn't set that up for the demonstration today. But absolutely, it's a key part of its character is having its camera.
And possibly our final question. Talk to us about the low pressure chamber testing and where was that done and that process.
Yeah, sure. So one of the really critical aspects of not just showing that Ingenuity would be able to fly on Mars, but developing all of the analysis and validating all the analysis that led to Ingenuity's success was the ability to replicate a Martian atmosphere here on Earth. And JPL has some really specialized facilities, in particular the 25-foot space simulator. And this is essentially a vacuum chamber. It's 25 feet in diameter, 80 feet tall. And the atmosphere can be essentially removed. It can be evacuated and then backfilled with CO2 to replicate what we're flying in on Mars. And so that was absolutely critical that JPL was able to develop that facility and show that Ingenuity could actually fly in this atmosphere.
Should we show some of the test articles that? Sure.
Yeah,
Let's come and.
You ask the next question.
Yeah, while you guys are doing that, we actually have, let's see. Does the low pressure on Mars cause the foam in the blades to expand and warp the blade?
No, it does not. So the engineering foams that we're using, these are closed cell foams. They're very rigid. They're actually able to maintain their structure within less than 1% of the expansion that what we have here on Earth's atmosphere. So it's really not a problem. We've tested that. We've shown that it's totally fine.
And then just talk to us about, a little bit about the solar panel on top. Is there anything that makes that special compared to other types of solar panels?
Well, so yeah, the solar array was built by the solar cells themselves were built by Solero, mounted onto the substrate, and the substrate was developed here at AeroVironment, and that's the carbon fiber and foam structure. It's built very similarly to the rotor blades. It is very special. It has to take the very harsh Martian environment. It needs to be very strong to survive launch. And it actually needs to have very specific natural frequencies and dynamics characteristics so that it doesn't interfere with the helicopter's control system. And so, yeah, that whole system was pretty highly optimized just to operate as the main power source for the helicopter and allow it to charge during the day.
Great. Um,
But if anybody wants to talk about the earlier models, we can do that.
Sure. Okay, so again, thank you everybody for your time. Thank you for the team for this incredible achievement and progress. I'm not sure if it was old age or distraction from these cool high technologies. I forgot to introduce myself. I'm going to blame it on the distraction rather than the old age. My name is Wahid Nawabi, and I'm the president and CEO of the company. So again, thank you for joining us today virtually as well as physically in our building. And good day, everybody.